Hi everyone, welcome to this second video on lesson 5 from atomic structure and periodic table. In this part of the lesson, I'm going to build on the picture of the atom that we gave to students in the first half, and we're going to do some practice of nuclide notation. So where we got to in the first part of the lesson, we gave students this picture and we built up from something very concrete. So I used a bottle of water. You could use anything. In the past, I've used like an oxygen tank or something like that. Something that students will be able to visualize, get them to think about it in a particle sense, so kind of year 7 science, then get them to think about it in a molecule sense, so what are the atoms within each particle. So that's really year 7 chemistry. And what we're doing then is zooming in on each one of those and saying, well, actually, according to Bohr's model, each atom looks a bit like that. So we're building their conception of atoms from very basic to a bit more complicated. So what I'm going to do in the second part of this lesson is take this oxygen atom, and I've redrawn it below. I've done the nucleus a bit smaller here to make it a bit closer to scale, although it's still, none of this is really to scale because the electrons, well, we know that electrons are hard to define at all, and the nucleus is super tiny relative to the size of the atom. But anyway, this is a relatively simple picture. And what I'm going to do is say, okay, this is an oxygen atom. Now, if I were to zoom in on the nucleus of an oxygen atom, it would look something like this. And what we want to do in this part of the lesson is show them exactly what it looks like. Now, the way I've found that is helpful here is building up before we get to the more abstract representation, which is the nuclide notation that we're teaching them about. So what I'm going to do is say, well, actually, oxygen atoms inside their nuclei, they have a certain number of protons. So I'm going to sketch some protons, and we can just tell students, actually, we know now, for reasons that they will find out about later, we know that oxygen atoms have 8 protons inside their nucleus. So I'm going to label each of these as a proton. I could also do it with a plus, just to emphasize that point about charge. And so I'm going to show that there's 8 protons inside the nucleus. And the next thing we're going to do is say, we also know, from that scientists have made, about the number of neutrons. Neutrons are a similar size, they've got the same mass, they just have no charge, so I'm going to do 8 neutrons. And I'm going to show students, I mean, I've maybe not done my circles big enough, these should be like super tightly packed in here. So the fact that there's some gaps in here is not the best. But how many have we got? 1, 2, 3, 4, 5, 6, 7, 8. I'm going to show that there's 8 neutrons in there as well. Now, the reason I'm drawing it like this is because I then want to start from my picture of the nucleus, which hopefully, because we've gone from water, something concrete, to increasingly abstract, and now we're inside the nucleus, we're super abstract here. What I want to do, though, is then move from this picture that they've got of what atoms look like to our more abstract symbolism. So in this case, I'm going to say, well, the way I would describe an atom of oxygen here is that because it's got 8 protons, I say it's got an atomic number of 8. And then that is, well, yeah, firstly, let's talk about that. That is what's called the atomic number. And you may wish to make a note here, or you can just tell students and then check on the whiteboards. I mean, giving you a definition of this is not that helpful. What matters is that they can use the idea of atomic number to work out how many protons and electrons there are. But you can tell them and write it down if you wish that atomic number tells us how many protons and electrons there are in the atom. So how many protons in the nucleus? It's 8. How many electrons in the total atom? It's 8. Okay. But again, that's not something that's necessarily going to stick first lesson. What we're going to do is keep coming back to this picture again and again and again and again in order to reinforce it in students' heads. So that's the atomic number. And then what I'm going to do is say, well, each of these has a mass of 1. we know that the mass of the electrons is almost nothing. So really, the mass of the atom is all in here. And to find the mass of the atom, I just need to count how many I've got in total. Now, I'm not going to count them all here. I'm just going to say, well, I said I had 8 protons, I said I had 8 neutrons. Therefore, I'd say I have what's called a mass number, and I'll label that here, mass number of 16. And then all I need to do to finish off the story is do the symbol for oxygen, which they will probably know, I hope, from just earlier years. The symbol for oxygen is O. And this is the notation that I need to do. So again, I could add here, it's the total number of protons and neutrons inside the nucleus, but I've tried to build it up from the concrete and move to that abstract definition of mass number, rather than giving them the abstract definition and then hoping they remember it. Now what I'm going to do next in this lesson is go through multiple examples, and I'll show you how I would do those. I just need to find those examples, I beg your pardon. So the first one here is helium, or the next one is helium. So that's another one that you could do. And again, if you wanted to start with a helium balloon or something and start with a helium atom, that's absolutely fine. So there we've gone from the kind of more concrete picture, let's say, we've tried to build up to the abstract formalism. What we're now going to practice is using the abstract formalism to build a more concrete picture. So if I was to do helium, like this, the first thing that I'm going to do is just remind students, I might cold call them, something like that, and just check that they remember that's the atomic number, that's the mass number. And I'm going to model, the way I tend to do this is as follows. I tend to say, what I can do with these numbers is work out how many protons, neutrons, and electrons there are inside the atom. Now the first thing to remember, that just tells us straight away the number of protons, and it also tells us the number of electrons. So before I do anything else, I can literally just look at that number and write in the number of protons and electrons in an atom. Obviously it's different when we get to ions, but we don't need to worry about that yet. What I do next is say, now I know that all of the mass, which is encapsulated in this number, is contained inside the nucleus. So the total mass, which is the total number of protons and neutrons, because each of them we give a mass of 1 using these atomic mass units. So the total mass is 4. And I like this layout. I find this really helpful because I just say, okay, I know that those two together equal 4. So what's that one? It saves me having to kind of do, like, write out all these awkward subtractions and stuff, because students just tend to be able to spot it. They go, okay, well, if it's 2 plus something is 4, that must be 2. Okay. Now you could leave it there and just do loads of practice on that, but I think it's also helpful to then, because we've gone from concrete to abstract to this notation, let's build it back up to concrete again. So let's look at what a helium atom looks like. Well, if this is my nucleus, I'm going to do this not to scale. What I'm saying here is I've got 1, 2 protons, and I've got 1, 2 neutrons. And then how many electrons we got? I've just got 2. And again, we don't need to worry about electron configuration and all that stuff yet. I'll say, and I've got 2 neutrons. And what's really important when you're doing this lesson is to keep moving from concrete to abstract. And I know this isn't concrete, this is still pretty abstract, but it's less abstract than this symbolic notation. And keep moving from one to the other and show how they map onto one another. So then, the further examples that you've got in the slides, next it goes to lithium and then beryllium, so we can just go through those. So these are nice examples because the numbers aren't the same, so they can't just guess these and hope for the best. And again, if we do P and E for this one, you might get students to do this on whiteboards, and some will make mistakes, and then you can kind of compare and give them the reasons why one is correct and one is not. First thing we do each time, we say, well, okay, the atomic number, that's just the number of protons, and that's the same as the number of electrons. These two together is equal to 7. What's the missing number then? 3 plus something equals 7, that must be 4. Likewise, I can do this next one about beryllium. Well, if I do P, N, E again, protons, neutrons, electrons, I can do 4. Electrons is 4, add the two together, and I get 9. 4 plus something equals 9. That means, that means I must have 5 neutrons. And again, go through those, and if you feel like the class needs it, draw the atoms out. Show them how this symbolism maps onto the picture of the atom that we're trying to build in their heads. So I think that should be relatively clear. The deliberate practice task is quite tricky. I would have a copy printed so you can go through a couple under the visualizer and model your thought process there as well. But hopefully once they've had lots of practice, and especially after this whole sequence of work where we're going to use these ideas pretty much every single lesson, students will have a really solid conception of this, and they'll be able to really think like chemists.